So we are in part 8, which is one of the most important part of our the study. So let us understand about stability of nonlinear system. Lyapunov's stability criteria is to analyze whether the system is stable or not. So what do you mean by stability? So in a very loose way, we can say that the system is stable if we start from somewhere, if we reach the origin, then we say the system is stable. If we start from somewhere, in many cases we may not reach the origin, we may be close to the origin, then also we will say it is stable. If we start from somewhere and if we approaches the origin, then we say it is asymptotically stable. And if we start from anywhere and if we reaches the origin, then we say it is globally asymptotically stable. So we require one abstraction. We should understand what is equilibrium point. Let us consider a nonlinear system. X dot is equal to f of x. Remember, x is a vector. So we will be considering x as x1, x2, two dimension in most cases. So what is an equilibrium point? Equilibrium point corresponds to point where x dot is equal to 0. So we will be considering the stability of the equilibrium point. Suppose we are in this state space, which is also called as phase plane or phase space. Without loss of generality, we will consider this equilibrium point, xc. We say system is stable if we start from here. If I reaches here, we say the system is stable. If I start from here, if I go away, we say the system is unstable. So this definition is not very precise. So this was one of the main contribution of Lyapunov. Lyapunov came up with first the definition of stability. I've been talking very loosely about three terms: stability, asymptotic stability, and asymptotic stability in large. Now we'll precisely put these terms. So let us understand what is stability or what is local stability. A system is said to be stable in the sense of Lyapunov if given epsilon, there exists delta such that if we start from a hypersphere of radius delta and if we remain within hypersphere of radius epsilon, then we say the system is stable. So to understand this definition, first we should understand one more mathematical concept, which is called hypersphere. So let me define first hypersphere and then I will restate the definition of stability. So what is a hypersphere? It's very simple. Hypersphere is a sphere of radius r. Hypersphere of radius r is a sphere of radius r. In two dimension it's circle. In three dimension it is a sphere. So let me draw it. In two dimension, if you consider a set of points, this is called a hypersphere. This will be denoting it as SR. So what is SR? SR is set of points such that norm of x is less than r. If I take any point in this sphere, its distance will be r. So I can tell the Lyapunov stability criteria in a very precise way, and not stability criteria, the definition of stability. Given epsilon, there exists delta, which is a function of epsilon, or I'll write delta of epsilon, such that all trajectories starting from S delta. What is S delta? A hypersphere of radius delta. from S delta does not leave S epsilon. Then we say the equilibrium point at the origin is stable. So let me draw one diagram. So given epsilon means we have a hypersphere of epsilon. What is the radius of this? Epsilon. Now there exists delta, which will be usually less than epsilon, this delta. So if I start from here, if I remain in this within this trajectory, if the trajectory is in this fashion, we say the system is stable. So if I start from here, the trajectory is like this, then we say the system is stable. Suppose we are given epsilon, there is another delta. If I start from here, if it goes away, then we cannot say the system is stable. So I'll repeat the definition of stability again. Stability or local stability in the sense of Lyapunov is a system is said to be stable if given any epsilon, however small it is, we will be able to find a delta such that all trajectories starting from S delta will not leave S epsilon. So here, this as a definition, as a mathematical concept, it is good. But suppose we have considered two examples in the last minute. That is, we took one trajectory from S delta, it was going out. We cannot say that system is not stable, because there may be another delta. If we start from another delta and if the system does not leave epsilon, then it could be stable. So that is the definition of local stability. Next we have asymptotic stability, which we will see in the next session.